Hi, this is Mrs. Ricard, and today I'm going to talk to you about solving exponential and logarithmic equations. So just as a reminder, an exponential equation is an equation that has a variable in its exponent. And a logarithmic equation is an equation that has a variable as the object of a logarithm. Now, we learned about exponents and logarithms together because they're inverse functions of each other. Like addition and subtraction, or multiplication and division, when you're solving, using one cancels out the other and lets you get the variable by itself. So that's what we're going to be doing with exponentials and logarithms. So if you're going to solve an exponential equation, the first thing you have to do is get the exponential expression by itself on one side. If there's more than one exponential expression, then you're generally going to either want to combine them if they have the same base, or get one on each side. Or you may need to convert them so that they have the same base. With a logarithmic equation, you're going to have to isolate the logarithm. So if you have multiple logarithms, you'll have to use the laws of logarithms to be able to combine them together into a single logarithm, or rearrange it so you have one log on each side. And then you're going to do the inverse operation. So if it's exponential, once you've got the exponential expression isolated, you're going to take a logarithm from both sides. If it's a logarithmic equation, once you've isolated the logs, then you're going to use an exponential expression. And what we're going to do is whatever the base of the logarithm is, we're going to use that number as the base, and we're going to use the two sides of the equations as the exponent on those bases. I call it exponentiating both sides on whatever that number is. In both cases, once you've done that, it will no longer be an exponential or a logarithmic equation. It'll be some other form of equation that we've already talked about. So now, let's take a look at our first example. 3 to the power 2x equals 80. You can see that 2x is in the exponent, so that makes it an exponential equation. The exponential expression is already isolated by itself on one side of the equation. So, since the base is 3, we're going to use log base 3 of both sides of the equation. On the side where we have the 3 as the base, log base 3 cancels out the base of 3 and just leaves the 2x. On the other side, I'm just going to leave that as log base 3 of 80. Then, to get x by itself, we need to divide by 2. So x would be log base 3 of 80. And that is an exact answer. Now, we don't necessarily want our answers exact. If you're using them for something, you'd probably want them as decimals. But from a math teacher's point of view, I want to know you're doing the process correctly, so I want to see the exact answers. If you want a decimal answer for this, then you can use your graphing calculator. And remember, if you don't have a graphing calculator at home, if you do not have an Apple device, because this is not compatible with Apple, but if you have an Android device, Wabbit Emu is a program that emulates the calculator. So we wanted log base 3 of 80 divided by 2. So we get our fraction template out. Common log is the one right there, but that's not what we're going to use because that is a log base 10. ln we're not going to use because that's log base e. But if we go to the math menu, let me move this down a little bit so you can see the keyboard. If we hit the math menu, and then we go to num So we use the arrow key to go over to num. And if you hit the up arrow, oh, maybe it must be under math instead of that. Sorry about that. There we go. Under math A, log base, if you choose that and hit enter, it's asking me for the base, log base 3. I use the arrows to move around in the template of 80 divided by 2. And I get 1.994. Remember, I ask you to round to 3 decimal places, so that would be 1.994 for the approximation. Now, there's another way to do this problem. Let's just take the answer to begin with. We learned that using the change of base theorem, if you had a log written in one base, you could change it into a log of another base. And you can use any base you want. Well, usually we're going to either use ln, which is the log base e, or we're going to use log with no number, which is log base 10. It's called the common log. It doesn't matter which one you use, but the change of base theorem says you take whatever log that you want to take of the object over that same log of the base. So you can also enter it into your calculator that way, or if you don't have a graphing calculator, then your calculator probably does have a log and an ln button on it so that you can find the approximations using it. And then remember, we were still dividing this by 2. So again, with the calculator, I'm going to get my fraction template, alpha y equals 1, and then I'm going to put natural log of 80, and close the parentheses, over 2 times natural log of 3. And notice I got the exact same answer that I got the first time. Now, a third way to do this is to use whatever log you want. You don't have to use log base 3 as long as you're consistent about what log you're using. So again, I had 3 to the 2x equals 80. So I'm going to take the natural log of both sides. Now on the left side, because I have this exponent on the object of the log, one of the properties of logarithms we learned is that it's equivalent if you bring this exponent down in front and multiply it by the log. So now, if we're trying to solve for x, that means we need to divide by the 2 and the natural log of 3 on both sides. So the 2 and the natural log of 3 would cancel, and we get x equals the natural log of 80 over 2 times the natural log of 3. And that is exactly the same thing we got by doing it the other way. Okay, our second problem. We have 20 times 100 minus e to the x over 2 equals 500. Now this time the exponential expression is not isolated yet. So the first thing we're going to do is divide by the 20. Because remember, because the 100 minus x over 2 is in parentheses, you can't subtract the 100 without getting rid of the parentheses first. So this 20 is just going to cancel with the 1 in the numerator. And 500 over 20 is the same as 50 over 2, which is 25. So now I have 100 minus e to the x over 2 is equal to 25. Now I need to get rid of the 100, so I'm going to subtract it from both sides. Remember, this was subtraction, but the 100 was positive, so you have to subtract it. So those cancel out, and now we have negative e to the x over 2 equals negative 75. Since both sides are negative, I'm just going to multiply by negative 1 on both sides to make them positive. And now we have the exponential expression isolated. It has a base of e, so I'm going to use the natural log for both sides. Now because the natural log has the base of e, the natural log cancels out the base of e and just leaves the x over 2. So then to get x by itself, we'd multiply by 2 on both sides. So these cancel and leave x. Normally we write the number that's being multiplied in front of the logarithm, so we don't get confused and think the 2 is multiplied by the 75. That 2 is not part of the object of the logarithm. So if we wanted to know what that was as a decimal answer, we'd put the natural log, sorry, got to get the 2 first, 2 times the natural log of 75. And that is 8.635, rounded to 3 decimal places. The third example of an exponential equation we have is e to the 2x minus 4e to the x minus 5 equals 0. Now this is clearly an exponential equation because we have variables in the exponents. But this one also looks kind of like a quadratic equation because you have something to a power, and in the middle term you have the same something to a power that's half of this power and a constant. So when we have a quadratic equation, we try to factor it to see what makes it equal to 0. Notice this side has to be 0 before you start trying to factor, because remember, the zero product rule doesn't work if you're not equal to 0. So if I split this into 2 parts, if I multiply e to the x times e to the x, that gives me e to the 2x. Just think about your properties of exponents. When you multiply 2 things with the same base, you keep the base and you add the exponents. The 2 numbers at the ends need to multiply to give me negative 5, and they need to add up to negative 4. Well, it's either going to be 1 and negative 5 or negative 1 and positive 5. 1 and negative 5 add up to negative 4, so I'm going to put plus 1 and minus 5. So that's factored. Now, because that product equals 0, I can set each one of the factors equal to 0. Now I need to isolate the exponential, so here I'm going to subtract 1 on both sides to get e to the x equals negative 1. And here I'm going to add 5 on both sides to get e to the x equals 5. One of the things we learned about exponential functions is that the base had to be positive. If this is a positive number and it's taken to any power, you can never get a negative answer because the range of an exponential, a basic exponential function, was from 0 to infinity. So this one, even if we try taking the natural log of both sides, so here the natural log and the e would cancel, getting x by itself. Sorry about that. And we get the natural log of negative 1. When we learned about natural log functions, we learned that their domain had to be greater than 0. So the thing we plug into that function can't be negative, so that gives us no solution for this part of the equation. For e to the x equals 5, we take the natural log of both sides, and that cancels out the base of e, leaving the x, and we get x equals the natural log of 5. So again, we get our calculator. and we put natural log of 5, and we get 1.609. Since the domain of exponential functions is all real numbers, there shouldn't be any problem with the solutions you get being actual solutions. But when we look at logarithmic equations, because their domain is not all real numbers, if we get a solution, it may not work, so we're going to have to check those solutions. So let's take a look at the logarithmic examples now. So our first logarithmic equation is log base 10 of the quantity z minus 3 equals 6. The log is already isolated on one side of this equation, and it's a log with base 10. So I'm going to use 10 as the base on both sides, and I'm going to make the two sides of the equation the exponent on both sides. I like to call this exponentiating on a base of 10. So the 10 and the log base 10 cancel out and leave just the z minus 3. And over here you have 10 to the 6th power. Well, 10 to the 6th power means you have 10 multiplied times itself 6 times, and that is 1,000,000. And then you would add the 3. And you get z equals 1,000,003. Now if you look back at the original problem, if you put 1,000,003 in here and you subtract 3, that gives you a positive answer. So it's okay to take the log. So 1,000,000 is 10 to the 6th power. Log base 10, the power you put on 10 to get 10 to the 6th power is 6. So this answer is correct. Looking at our second example, we have log of x plus 4 minus log of x equals log of x plus 2. Now notice our logs don't have numbers on them, which means they're the common log, which is base 10. On this side, we don't have a single logarithm. We have two of them. We have a different one on this side. We could put them all on one side and combine them, but I think it's going to be just as easy to leave this the way it is, but we have to combine these two into a single logarithm. So when we discuss the properties of logarithms, we learn that if you're subtracting two logarithms, it's equivalent to taking the log of their quotient, as long as that log had the same base. So log of x plus 4 minus log of x is equivalent to just having log of the quantity x plus 4 divided by x. So now I have a single logarithm on each side. Since it is a log that's base 10, we're going to exponentiate on a base of 10. So again, that means I'm going to use 10 as the power, as the base, and I'm going to use the two sides of the equation as the exponents. And the whole reason you do that is when you have a 10 to a common log of something, the 10 and the common log bounce out, and you're just left with x plus 4 over x. And on this side, the 10 and the common log cancel out, and you're just left with x plus 2. So now it's not a logarithmic equation anymore because it doesn't have a log in it. But when we have an equation that looks like this, first we want to get that x out of the denominator. It's important to remember, though, that since x was in the denominator, you have a restriction that x cannot be 0 in your final answer. So to get x out of the denominator, I'm going to multiply by x on both sides. So on this side it cancels and I'm left with x plus 4. On this side I distribute and I get x squared plus 2x. because the highest power of x is 2 in this problem, that means it's a quadratic equation. So we want to get 0 on one side. So I'm going to subtract the x and the 4 from both sides. So over here, these canceled out, leaving 0. And now I have x squared plus x minus 4. Well, when we have a quadratic equation in standard form, we want to factor it if we can. This one has a leading coefficient of 1, so if we're able to factor it, that means we're looking for factors of 4 that subtract to give us 1. Well, one factor pair of 4 is 1 and 4, but those don't subtract to give you 1. And the only other factor pair of 4 is 2 and 2, and those don't subtract to give me 1. So that means this one is not factorable. But that doesn't mean you can't find the solution, because you can also either complete the square or use the quadratic formula. Well, when I use the quadratic formula, I like to check the discriminant first, b squared minus 4ac, because if that comes out to a positive perfect square, that means I could have factored this. Now I know it's not going to, but I need this quantity in the quadratic formula, so I might as well do it separately and make it a little simpler to deal with. So in this equation, b is 1, a is the coefficient of x squared, so it's 1, and c is the constant term, so it's negative 4. So this gives me 1 plus, because the minus and the negative cancel, 16, which is 17. So for the quadratic formula, which is x equals negative b plus or minus the square root of b squared minus 4ac, all over 2a. We now can plug in our numbers. So b again was 1, so negative b is negative 1. b squared minus 4ac was 17 from our calculations over here. And 2a, a was 1, so 2a is 2. So this is actually giving me two possible answers here. Negative 1 plus the square root of 17 divided by 2, and negative 1 minus the square root of 17 divided by 2. Now, remember what I said about having to check the answers for logarithmic equations. The square root of 17 is a little bit more than 4. Negative 1 minus about 4 is about negative 5. Divided by 2 is a negative number. And if you look back at our original problem, if we have a number that's about negative 5, that gives us a negative object here of about negative 1, a negative object here of about negative 5, and a negative object here of about negative 3. And logs can't have negative objects. So that answer where we subtracted the square root of 17 cannot be a solution. But we still should check this one. Negative 1 plus a little more than 4 is about 3 divided by 2. So I want to check this one, but I want to use the exact value of this to check it, because if I use a decimal approximation, it won't come out exactly correct. So on my calculator, I'm going to put that number and I'm going to store it into a variable, and then I'm going to go back and I'm going to put this equation, well, the two sides of this equation, into my calculator separately and see if they come out the same. So, excuse me, my number was, I'm going to use the fraction template, negative 1 plus the square root of 17 over 2. And I'm going to store that into x. So now the left side of my equation, I'm just going to scoot that down a little so you can see, was log of the quantity x plus 4 minus common log of x. So common log is the button on the calculator that just says log. It's right there. So log of the quantity x plus 4, close the parentheses, minus log of x, and again close the parentheses and hit enter. So that came out to 0.5516 whatever. Okay? And now I'm going to do the right side of the equation, which was the log of the quantity x plus 2. And notice I do get the exact same answer on the calculator. So that means that answer is correct. For our third example of logarithmic equations, here I have log base 3 of x plus log base 3 of x squared minus 8 equals log base 3 of 8x. Now again, I can't exponentiate until I have a single logarithmic expression on this side. So since the two logs are added, the properties of logarithm tell me that I can write that as the single log with the same base of their product, which is x times x squared minus 8. So now, since this is a log base 3, I'm going to exponentiate on a base of 3. Now, I saved myself a little writing by just putting a 3 down here below, so it's like 3 to this side equals 3 to that side. And the 3 and the log base 3's cancel out on both sides, and that leaves us with x times, x squared minus 8 equals 8x. So now, it's no longer a logarithmic equation, so I'm going to multiply through here. That gives me x cubed minus 8x equals 8x. I'm going to get everything on one side, so I'm going to subtract 8x from both sides. That gives me x cubed minus 16x equals 0. I have a common factor of x, which leaves me with x squared minus 4. And x squared minus 4 is a difference of two squares. Sorry, x squared minus 16. I was getting ahead of myself there. And so the factorization of a difference of two squares is the sum of their square roots times the difference of their square roots. And now, since the product equals 0, we set each factor equal to 0. Well, x equals 0. Remember, we have to look at our original equation. Up here, I would have log base 3 of 0, and the object of a logarithm has to be positive. It can't be negative or 0. So right there, I can eliminate that solution. With this solution, I would subtract 4 from both sides, and that gives me x equals negative 4. Well, there again, I can't plug a negative number into this log base 3 of x. So that's not a solution. If I take this one and I add 4 to both sides, I get x equals 4. Well, that's not going to be a problem plugging it in here. Log base 3 of 4, it's a positive number. Here, 4 squared is 16 minus 8 is 8, so that's a positive number. And here, 8 times 4 is 32, so that's a positive number. Now we just have to check to see if it works. So we have, I'm just going to do that below here, log base 3 of 4 plus log base 3 of 4 squared minus 8 equals log base 3 of 8 times 4. Well, 8 times 4 is 32. 4 squared is 16 minus 8 is 8. So we have log base 3 of 4 plus log base 3 of 8 equals log base 3 of 32. The properties of logs say that, I didn't write the 4 there, sorry. If we add two logs, that's the same as taking the log with the same base of their product. 4 times 8 is 32. And notice that that means the equation is true. So x equals 4 is a solution. Okay, the final example, we have the natural log of the square root of x plus 2 equals 1. Now before you even start, you need to remember that square roots can be written in exponential form. And that's the first thing we're going to do. Natural log, and instead of saying the square root of x plus 2, remember the power is the numerator and the root is the denominator. So this is x plus 2 to the 1/2 power equals 1. Using the properties of logarithms, this 1/2 can come down in front and be multiplied by the logarithm of just the object, plus 2, x plus 2. Now I want to isolate that logarithm, so to get rid of the 1/2 that's multiplied by it, I'm going to multiply by 2 on each side. So these cancel, leaving the natural log of the quantity x plus 2. And over here we just get 1 times 2, which is 2. Now that the log is isolated, it's a natural log, so its base is e. So we exponentiate on a base of e by using e as the base and the equation as the exponents. The e and the natural log, since they're of the same base, cancel, leaving x plus 2. And on the other side we just get e squared, and you can just write e squared. And then all that's left to do is isolate the x by subtracting 2 from both sides. So that gives us x squared equals e squared minus 2. To check this one, again, we go back to the original equation. So we have the natural log of the square root of e squared minus 2 plus 2 equals 1, because e squared minus 2 replaces the x, but that plus 2 is still there. Well, the minus 2 and the plus 2 cancel. And then we get the natural log of the square root of e squared equals 1. Well, the square root and the squared cancel out, so that's the same as the natural log of e equals 1. And when we see a natural log, we think the power I put on e to get e is 1. So that one is also true. Now once again, if you wanted the decimal answer for that, you would simply put it into the calculator. Sorry about those. So e to the power is second natural log squared minus 2. Whoops, didn't get out of the exponent, sorry about that. Out of the exponent, minus 2. And that is 5.389 to 3 decimal places. So I hope you had a good time understanding that, and I'll see you the next time. Thank you.